Good day to all of you. My name is Dr. Naren Selvaratnam, and this video is about how to run a simple linear regression. Now, if you are new to my channel, I would encourage all of you to go through my research playlist. There's quite a lot of videos about correlations and descriptive statistics and other forms of inferential statistical analysis as well. But in particular for this lesson, I think if you could go through the previous lesson on correlations 1, that's the theoretical bit of correlations, and then correlation part 2, which contains the computational aspect of a correlation, I would encourage you to go through those two videos before starting the video on simple linear regression. Now, with that being said, let's try to understand why exactly regressions are important and what are the learning outcomes of this session. Now, the first is to understand the basic statistical procedures involved in simple linear regression, and also how to perform a linear regression, not just in SPSS, but I mostly use Jamovi these days. So I'm going to show you how exactly you can do this in Jamovi, and then how exactly the interpretation of data would work. So this would also have some assumptions. You need to meet some assumptions to do a simple linear regression. So in this video, we will focus on those assumptions as well. Now, these are the formulas that you need to have in order to run a simple linear regression. Starting with this is the equation that we use to come up with the values to plot the best fit line. Now, if you don't understand what the best fit line and why exactly we do all of this, it will be covered in the next few minutes and as we go through our slides. But these are the formulas. So this is the main formula, y equals bx plus a. Here b is derived through sum of products and sum of squares x, and a is derived through mean y minus slope times mean x. And then SS regression and SS residual and MS regression and MS residual, these are once again formulas that you need to have in order to run a regression, but we'll come there. But before we go through all of this, let's try to get a bit of an introduction as to why this is important and what exactly regressions generally are. Now, if you have learned about correlations, you know correlation is something that you use to demonstrate a association between two variables. For example, those who do well in SAT, that is the Scholastic Aptitude Test, could do well in the university as well. So SAT and GPA has a correlation. But what if you want to actually go ahead and make a prediction? So a particular SAT score could help you determine what kind of GPA is expected for a particular student. Now, in correlations, you don't make such predictions, but if you have that data, we can, of course, in correlations also, if you draw a scatter plot, you will get a best fit line. But here, what we do is we are going to work on the method of getting this best fit line, and then we are going to use that best fit line and the equation that comes along with it to make a prediction about what exactly the score for y is going to be, provided that x is a particular value. Let's say if someone's SAT score is, let's say, 700, what is exactly going to be their GPA. So that is something we can predict once we run a regression. But if anyone of you would want to know how to run a very basic simple linear regression, if you use Jamovi, you can enter the data. You need to have two continuous variables. Here I have put self-efficacy and anxiety data. If you go and click on analyze, and then it gives you a drop down from there. If you select linear regression, it will give you a set of options like this. So you have to transfer your dependent to the dependent variable and the predictor to the covariates. And on your right side, you would notice the model fit measures and then model coefficients. So this is the output that you get by default without clicking on anything else. The moment you transfer your variables to the right side, it will generate this output. Now, based on this, you can see there's R value, and then there's the correlation, and then here you have the R square, that's the effect size, coefficient of determination, and then here you have the p-value to see whether this is significant or not. So yes, self-efficacy do have the capacity to predict anxiety, but it's not that strong. And you can also know it is not strong because the effect size is pretty low, as it is 0.07, so roughly about 7% of the variance in anxiety is accounted by self-efficacy. So rest of the 93% of the times it could be something else. So this is once again the same output. Here you have I have given the ANOVA test output as well. Once again, it gives you the F statistic and the p-value, but this will be much more clear to you once we go through the exact workings and once you understand how exactly this computation comes into being. So let's try to understand what regression is now. Pearson correlation is a technique for describing and measuring linear relationships. Now you should know what a linear relationship. Linear relationship, it has two variables where, let's say, x and y variables. So every increase in x is supported or would contain another increase or decrease in the y as well. For example, SAT and GPA. Now the question is, why should we draw a line in the middle? Now in correlations, drawing a line would show the strength of the correlation, the direction of the correlation, and through that you can see whether the data points are falling on top of this line or whether they are scattered away. Usually if the slope is taking a shape of a diagonal, the normal correlation, generally speaking, the points tend to fall closer to the line, so indicating that's a stronger correlation. And at the same time, like I mentioned, this line identifies the central tendency of the relationship. So how far away the points fall on top of this in relation to this best fit line. Ideally, if the correlation is good, the point should fall closer to the line. So that's the basic idea here. So to determine how exactly this relationship works and to get this best fit line, you need to come up with the equation. The equation is y equals bx plus a. Here a and b are constants. A is the intercept and b is the slope. Now let me give you another example here. SAT score of 620 corresponds to a GPA of 3.25. Thus the college admissions office could use the straight line relationship to predict that a student entering college with an SAT score of 620 should achieve a college GPA of approximately 3.25. If you notice right here, this is the best fit line, and you see x here is the SAT score, y is the GPA, and for every x value there's a y value as well, and not every point is falling on top of this line, but this line is the line that could best describes the relationship between these two variables. So since some points are a little far away and some points are falling on top, there's a standard distance between this line and the points as well, which is something that we need to find if we need to do a regression analysis. But in a correlation, you would get a scatter plot just like this. But we don't use the relationship to make a prediction for data that is not available here. So what happens in regression is, if someone says, okay, look, now this is the relationship, and if you use the y equals bx plus a equation, through that you can of course make a prediction about what if someone has a SAT score of, let's say, 675, what exactly is going to be the GPA. So using this equation you can actually make that as well. So this is the linear relationship that we were talking about, y equals bx plus a. Here you have x and y. Now let's go through a much easier example here. A local tennis club charges a fee of $5 per hour plus an annual membership fee of $25. So with this information, the total cost playing tennis can be computed using a linear equation. The total cost here is denoted by y. Now 5 here is the slope. For every additional hour, there's a cost of $5. X is the actual number of hours. So if it is 1 hour, so then you have to substitute 1 instead of x. If it is 10 hours, you have to substitute 10 instead of x. And 25 is the intercept. Even if you play or not, there's a particular payment of $25 that you would have to make. So when x is 0, y is still at 25. So if you plot this, it would so I don't have the plot here, but if you plot it, it should look something like this. It should start at 25. So let's try to solve this equation. If you want to know how much you need to play for 10 hours, so 5 times 10, so you substitute 10 for x and then plus 25, so that should be a $75. So using this equation, you can make that prediction. So the statistical technique that you use to find this best fitting straight line for a set of data that is given, we call it regression, and the line is called the regression line. Now, the goal in regression is to find this best fitting straight line. However, you should always keep in mind it is necessary for you to define precisely what is meant by this best fit. To determine this best fit, you need to determine the value for B and value for A in a given relationship. But before we go through that, let's try to understand how exactly we are going to find this relationship. To determine how well a line fits the data points, the first step that you need to do is to calculate the distance between the original or the actual y value and the predicted y value. The predicted y value is denoted by y hat, this one right here. So that's the value that will be we will be using to draw the best fit line. The normal y is the actual y that you have. If you have two variables named x and y, the y is the original y that you have collected from your data collection. In relation to that, you have to find the y hat value for every y value, and through that you can find the distance between the actual data point and the predicted data point. So predicted data point is the point in the best fit line. So this distance is y minus y hat. But when you do this calculation y minus y hat, some of the resulting values would be positive and some of them could be negative. So what we do is we actually square them. We square them and then we get the sum of all of that, so sigma of all of it, and then we can actually get the residual sum of squares for residuals. Now we can go through that. So this sigma y minus y hat squared, so y minus y hat, that's the standard distance. Since the resulting output could be negative and positive, we need to square it up, and then we take the sum of it, and that's what we call the total squared error. This total or the least squared error solution is exactly what we need to find the distance between the points and the actual data points and the predicted data points. So we can define the best fit line as the one that has the smallest total squared error. So you may have different types of best fitting lines, but the best fitting line that we are interested here is the one that has the smallest total squared error. So we go for that, and this least squared error solution has to be utilized to do our calculations. Now in symbols, we are looking for a linear equation in the form y hat equals bx plus a. So this becomes y hat because we are interested in using this least squared error solution for our equation. So the general equation for a regression is y equals bx plus a, but what we are interested in finding is the best fitting line. The best fitting line, like we mentioned, is the distance between the actual data points and the predicted data points, which is denoted by y minus y hat squared, the sigma of y minus y hat squared. So because of that, the values that you need to generate for your y hat, or the values that you need to generate your best fit line, for that you need to use this equation y hat equals bx plus a. So for each value of x in the data, the equation will determine the point on the line, that's the y hat. so which can gives the best prediction of y when x changes. What exactly is going to be the score for y can be predicted using this particular equation. But before we go through this, before we find the corresponding y hat data for every y, we need to determine what is b and what is a. So to determine what is a and what is b, there's an equation. B can be found through sum of products divided by sum of squares x. Sum of products can be calculated pretty easily. So the same is applied for sum of squares x as well. And there's the alternative formula as well, but this alternative formula requires you to have Pearson correlation. So I'm going to stick to this because this can easily be calculated. And then A, the equation is mean y minus slope times mean x. And then you can, once you find the value for B and A, then you can find the values for the predicted y, or the predicted scores for y. That is something that you can do with this y hat. So now see, now here you have x scores, here you have y scores. The mean of x is given here, that is 4. The mean of y is given, that is 8. The sigma of all of this is 32, that is sigma x. Sigma y is 64. So x minus mean x, for example, 2 minus 4 is minus 2. So likewise you can do it for the entire x column, so that is x minus mx, and you can do the same for y, that is y minus my. So this 2 minus 2 times minus 5 is equal to plus 10. That's the sum of products. X minus mx times y minus my is the sum of products. So when you get the sigma of all of that, you get the sum of products, that is 36. At the same time, sum of squares would be x minus mx, once again, squared. So sigma of x minus mx squared, that is exactly the sum of squares for x, SSX, that is 36 as well. So the calculation for B is sum of products divided by sum of squares x. Since sum of products is 36 and sum of squares for x is 36, the answer is going to be what? It's going to be 1. See, this is the score for B. Answer is 1. And for A, it's going to be 4. Mean y minus slope times mean x. Now you can actually calculate the y hat for every x value. So for example, if you substitute the b and the a here, our equation is going to be y equals x plus 4. Now our b is 1, so it's going to be actually 1x plus 4, but 1 is actually not needed. Why? Because whenever you multiply something by 1, it's going to be the same, so you don't need to actually include it. So y hat equals x plus 4. The relationship would look like this. 4 is the intercept, so even when x is 0, there is still y at 4. So y would always start at 4 in this particular plot, and then it would have a upward momentum or upward trend, just like what you see. So if a set of data has no deviation from the best fit line, then the data points would appear to be on the top of this best fit line. This is the best case scenario. Usually you would never see points falling on top of this line. Not all the points, you might see some points falling on top of the line, but if you have all the points falling on top of the line, that's a perfect relationship. That kind of perfect relationships are usually very difficult to be found. So because of this, we need to identify what's the standard distance between the data points and the best fit line, which is something that we can do through the standard error estimate. So through the standard error estimate, we find the average deviation for the data points from the best fit line, kind of like the standard deviation. See, now in this equation, y equals x plus 4, the data, none of the data that you see here falls on top of this line. compared to this point right here, there's a smaller distance between the best fit line and this point. But compared to that, this one has more distance. This one has even further distance. But this best fit line is the line that is best fitting the data that we have. But still, from this best fit line to this data point, there's a smaller distance. So we need to calculate the standard error estimate to find what this distance is. So this distance can be calculated by first getting the sum of squares residuals. Sum of squares residuals is the sigma, or the total of y minus y hat squared. Y minus y hat, that's the distance between the the best fit line and the actual y, the actual data points and the predicted data points. So you have to square this up and then sum it all up. Then you would get SS residuals. So these SS residuals have to be divided by the degrees of freedom, and then you have to take the square root of it, as demonstrated here. Square root of SS residuals over degrees of freedom. And then once you get that, you will get the standard error estimate. So how are you going to do this? Now let's try to understand all our equations here and how we have done this. Our equation is y hat equals x plus 4. How did we come to this? Based on the data that you have x and y. The first step is to find the x minus mx, y minus mx, my, and then sum of squares for x, and then the sum of products. When you have all of this, you can calculate the sum of products and sum of squares x, and basically using this you can calculate the value for b, and using the values you can actually calculate the value for a as well. Once you calculate b, using the b value here, you can calculate a, and then once you substitute b and a for the equation y equals bx plus a, you get the the equation here for this analysis, that is y hat equals x plus 4. Now y equals x plus 4, so get all these y values, okay, and sorry, these x values. So now you have to calculate y hat for every x value. So then substitute every x value here and add 4, and then you can get the y hat value. So for example 2, if you put 2 instead of x here, y hat is 2 plus 4, that is 6. Here x is 6, so then y hat should be 10, because you are using this equation to come up with these y hat values. And when you have this is the y hat values. So now what you need to do is you need to calculate the distance between the y and the y hat. Y is here 3 minus y hat 6, that is going to be negative 3. This is the distance between the actual data points and the predicted data points. So you need to take the square of this. Minus 3 times minus 3, that is 9. Likewise, you do this calculation and then you sum it all up. Sigma y minus y hat squared, that's the SS residual, so that is 28. So this SS residual is something that you need to keep with you to do the rest of the analysis. Now let's calculate the standard error estimate for the equation y equals x plus 4. Here the SS residual is 28 and our sample is 8. So n minus 2, our degrees of freedom is going to be 6. So this is our equation, square root of SS residual divided by degrees of freedom, that is 28 divided by 6 square root. So the answer is 2.16. So the standard distance between the actual data points and the regression line is measured by this, which is 2.16 in this example. So this standard error is related to the magnitude of the correlation between x and y. You have to have this value as smaller as possible to have a strong relationship or a strong correlation. If the correlation is near plus or minus 1, the data points will be clustered very close to the line, and the standard error of estimate is going to be extremely low. But if you have a higher value for standard error estimate, what it means is your correlation is not so good. So this is our equation, this is how it is plotted. So the average distance between this best fit line and the points is 2.16, that's the standard error estimate. Now when you have this, the next bit is you need to find the predicted variability and unpredicted variability of your data. This is important for your regression calculation or the final formula. So coefficient of determination, that's the effect size we usually do calculate in correlations. Once we run correlations, so you square the correlation coefficient r squared, that's the coefficient of determination, which explains the proportion of y that is explained by x. So predicted variability can be explained through r squared. So the unpredicted variability can be explained by 1 minus r squared. So here the predicted variability is what we call SS regression, which is calculated by r squared times sum of squares y. SS residual, that is something you can calculate through 1 minus r squared times sum of squares y. So you have to then calculate sum of squares for y as well. I have given the calculation here, and you have to calculate the Pearson correlation as well. Pearson correlation is sum of products divided by square root of sum of squares for x times sum of squares for y. And then once you do that, you have a few more numbers with you to go ahead with the rest of the calculation. So Pearson correlation, here we have done the simplification. So sum of products divided by square root of sum of squares x times sum of squares y. So the answer is 0.75. That's a good correlation. It's a stronger correlation as well. Now let's calculate the predicted variability, that's the SS regression, and unpredicted variability, that's SS residual. SS regression is r squared times sum of squares y. So the answer is going to be 36. SS residual is 1 minus r squared times SSY, the answer is going to be 28. Now once you have all of this, you can actually go ahead and do your final calculation. So when we get a correlation, we can use regression to see whether there's a significant relationship among the variables or not. So regression equation is very similar to the ANOVA. So F equals MS regression divided by MS residual is our equation. MS regression has a degrees of freedom of 1 and MS residual has a degrees of freedom that is n minus 2. So in this case that is 8 minus 2. So the answer is 6. So you have to come up with the hypothesis. So I have given a null hypothesis here. The regression equation does not account for significant proportion of variance in y scores. And then if your confidence interval is 95, you have to come up with an alpha value that is 0.05. So based on this alpha for degrees of freedom of 8 and sample of 8, where the numerator df is 1 and the denominator df is 6, you have to locate the critical value in the F distribution. So this is the distribution. You can find the numerator and the denominator. So your value is here, that is 5.99. So I would encourage you to go through this distribution, the values, so that you can see how exactly that you are going to select this value. And then you can compute the statistics. So the predicted variability is 36, we found, that's the SS regression. Unpredicted variability, that's the SS residual, 28. So MS regression is SS regression divided by degrees of freedom regression. That is 36 divided by 1, the answer is 36. MS residual is SS residual divided by DF residual, that is 28 divided by 6, so answer is 4.67. So the final equation is F equals MS regression divided by MS residual, so that is 36 divided by 4.67, that is 7.71. Now you need to see whether this 7.71 falls beyond 5.99. So yes, with the critical value of 5.99, we reject the null hypothesis and conclude that the regression equation does account for significant proportion of variance in the y scores. Why? Because 0.71 folds beyond 5.99. So I did a bit of a SPSS calculation as well. So the correlation is 0.750, and this is the correlation. R squared is 0.563. Standard error estimate we have here 2.1. Here you have the F value, numerator DF, denominator DF, significance. And here you have the ANOVA output as well. And this is how your output should look like. The narration, APA style. The overall regression was statistically significant. R squared equals 0.563, comma, F numerator DF, denominator DF, F value, and the P value. So there are some assumptions that we need to discuss as well. So let's discuss those assumptions before we proceed further. But with this, you should have an understanding how this regression works. So this is exactly how the regression works. Of course, running a regression with just your software is pretty easy. But what you need to do is you have to have an understanding that there's going to be some other analysis, so internal workings here, so that this will help you know more about the terminology when you go through regression output in software, because you might see the word residual always when you especially run assumptions and all of that. So you need to know what exactly is meant by residuals. That's why we have to go through all of these steps so that you would have a better understanding.